In the last video, we talked about periodicity of Markov chains, and specifically periodicity of classes of states. In this video, we're going to be talking about positive recurrent states or classes. Now, you might recall seeing this word recurrent. So in another video, we had talked about recurrence as whether or not you return to a node or a state. Sorry, so I use those node and state interchangeably. So if you started in state 1, will you at some point get back to state 1? Now, positive recurrence not just asks, will you get back to state 1, but how long will it take for you to get back to state 1? So again, let's imagine this was like happy, sad, confused. We might ask, well, if we're happy, on average, how long will it take before I'm happy again? Right. Or another good one is, let's say these are sales at your favorite store. So maybe state 1 is a BOGO, state 2 is nothing, state 3 is like 25% off. One big question you might have is, hey, I just missed the sale. How long will it be until they do another BOGO? And so maybe you can model that as a Markov chain if we have the probabilities. All right. So this is what we're going to be focused on for positive recurrent states. A positive recurrent state is one where the time it takes to get back to the state is finite. Okay, so it has an actual number. It ends up, there are some cases where it might take infinity time to return back to a state. Now, for our case, when we have a finite Markov chain where we have a set number of states, we will almost always be positive recurrent for any recurrent states that we have. Okay. So maybe in another video, I'll show you an example of states where it's not finite. So the drunk man's walk or the random walk, right, where the guy can go left or right, that would be an example where you might have an infinite state set. Now in this case, we have a finite set. Okay, so what we're going to do is I'm going to sort of work through an example problem of how we calculate, let's say, how long it takes to go from state 2 back to state 2. Now, in order to do that, we're going to need to define a few terms. Right? So actually, let's start by writing the question. So the question is, how long does it take to return to state 2? And this assumes that you're starting off in state 2. Right. So in order to do this, we're going to define just a couple terms or variables that are going to help us sort of work through this. So the first one is going to be H2. Okay, and this is the one that we're really going to care about. So this is if you're at state 2, how long does it take to return to state 2? We're also going to define H1, which is if you're at state 1, how long on average does it take to get to state 2? And then finally, we're going to add H3, which is if you're at state 3, how long on average does it take for you to get to state 2? Now, the reason why we're introducing H1 and H3 is because we're going to be able to define H2, so how long it takes to go from 2 back to 2, in terms of these two quantities. And more specifically, what we're going to end up with is with a system of 3 linear equations and 3 unknowns where we can solve for H1, H2, and H3. Now, again, the important one that we want to solve for is H2. All right, so let's sort of work out how we can do this. All right. So I'm going to start at state 1, and I'm going to ask, how long does it take if I start at state 1 for me to get to state 2? Now, there are 2 ways we can do that. We can take one step and get there directly to state 2, or we can take one step towards state 3 And then we got to figure out, well, how long does it take to go from state 3 back to 2? All right. So the way we can sort of write this mathematically is we can say, well, we're going to take one step. After we take that one step, how many more steps do I need? So if we take that one step to state 2, we do that with 1/2 probability. The number of additional steps that we take is 0 because we're already at 2. Right. Now the second option is, with 1/2 probability, we end up taking a step towards state 3. So in that case, we now have to say, well, if we're at state 3, how long does it take for us to get to state 2? And we can just use the variable we defined, h3. Okay. And so now we have an equation of how long it takes to go from state 1 to state 2 based on h3 and based on the fact that we could go directly from 1 to 2. All right, so now let's look at h2. Okay. So again, we're going to say, well, we could take one step. Now, we might take that step from 2 to 1. Okay. In that case, that will happen with 1/3 probability. All right. And the time it will take to go from 1 back to 2 will just be given by h1. The other option is, if we start at state 2, we take that step with 1/3 probability back to step 2. And then we don't have to do any other additional steps. So we're going to get 1/3 times 0. And lastly, we have the option that with 1/3 probability, we take a step to 3. And then from 3, we have to figure out how long it's going to take to get back to state 2. All right. So at that point, we have h3. So we can repeat the same thing for state 3. We're going to take one step. With 1/2 probability, we're taking that step to state 1. And then from state 1, we have to calculate or figure out what the expected time is to get to state 2. And so with that, we can just write h1. With 1/2 probability, we stay in state 3. And so we end up just writing 1/2 h3. So at this stage, we have 3 equations with 3 unknowns. And if they're linearly independent, we can actually solve for them. So in order to do this, I'm going to go ahead and write this in matrix form. Hopefully you guys remember how to do that. I'm going to put all the constants on one side and all our variables on the other. And we're going to want to rewrite the equation like ax equals b. All right, so let's go ahead and do that real fast. So I'm going to move all the 1's to one side and all the h's to the other. And so we end up with the following. So this equation becomes minus h1 plus 0h2 plus 1/2 h3. Yep. All right, our next equation, and this should be a -1. -1 equals 1/3 h1 minus h2 plus 1/3 h3. And finally, we have -1 equals 1/2 h1. And then we're going to subtract these two from each other. We get -1/2 h3. All right, so let's go ahead and put that into matrix form. So in this case, we end up, our A matrix is equal to -1, 0, 1/2. Here we get 1/3, -1, and 1/3. And finally, we get 1/2, 0, -1/2. We're going to be multiplying that times h1, h2, h3. And that's equal to -1, -1, -1. What was that even read? Okay. All right. So once we have this matrix equation, all we have to do to solve for h1, h2, h3 is take A inverse and multiply it times B. All right, so once you guys do that, I'm going to pause the video. And then when we get back, hopefully we have the same solution. So go ahead and... So actually, I forgot to tell you how to do this in Octave. If you're doing this in Octave, what you're going to want to do is just say A equals whatever the matrix is. B is equal to -1, -1, -1. And then in order to solve for x, you can say x equals INVA times B. Okay, so this is how you would do it in Octave. All right, so hopefully you've entered in A and B, and you can do that. And when you solve for it, I think you should get something like 4.333, repeating, and then 6. And so what this tells you is how many time steps it takes to go from 1 to 2 on average, to go from 2 back to 2 on average, and then from state 3 to 2. Okay, so again, this is how long does it take to go from 1 to 2? So in fact, sometimes you'll see this gets written a few different ways. So maybe we can be a little bit more clear. This is the expected time. So sometimes you see people write it as tau of 1 to 2. All right, and this expected time is a random variable. The next one is the expected time from 2 to 2. And this is the expected time from 3 to 2. Okay. Now, I wrote these as random variables, so these taus are times. Okay. Now, we do have a standard notation for what we call these expected values. And we call them mu's. So here we have mu1, 2, mu2, 2, and mu3, 2. All right, so quickly, let's sort of look at what ended up happening. So I told you a Markov chain or a class of states in a Markov chain are positive recurrent if the expected time to return to that state is finite. So let's look at this. So I started by asking, how long does it take to return to state 2 if you started in state 2? Okay, so we're starting in state 2, and we want to know how long it takes to get back. We wrote a whole bunch of equations. We solved for them using linear algebra. And we basically said, hey, the time it takes to get back, on average, is this mu22. Okay? And it takes 4.33 steps. Okay? So the answer here is mu22 is 4.333. If you want dual bar, sure, why not? Okay, so box your answer because it's important. Right. Now, the great thing about periodicity and recurrence, or positive recurrence even, right, is that they're class properties. So if I know state 2 is positive recurrent, in this particular case, I know that state 1 is positive recurrent and state 3 is also positive recurrent. And the reason I know that is because they're all part of the same class. Okay, so 1, 2, and 3 are part of the same class. So if I know, again, I see it's state 2 is positive recurrent because this isn't infinity. It's a finite number. We can calculate it. Then 1, and 3 must also be positive recurrent. And sure enough, if you want, we can go through a whole bunch of equations to figure that out. Okay, so but all we're going to need to show is that one state is positive recurrent. Cool. So again, yeah, let's end there. Let's go.